All right, so this is linear programming, lecture 26. The desks continue to move further and further back. Hopefully, we will finish the semester before you guys are outside because it's going to be snowing. Actually, I think I have to move this a little bit closer because it's not too far away. All right. So the main goal today is to try to prove either Brouwer's fixed point theorem, or if we don't quite get there, at least start introducing some of the notation. Okay. So the first question is always, what kind of space do you want to study? So a lot of what we're going to do today is barycentric coordinates, and we're going to be looking at simplices. Basically, think of them as line segments, triangles, pyramids, extensions like that. Are most of the spaces you look at like this? No. Right? Most of the spaces in the world are not triangles or simplices. The question is, how much do they differ? Is there a nice mapping between them? So let's say we have f from S to T is an isomorphism. If there exists, well, actually, let's use phi. If there exists f with a fixed point on S, is there a G with a fixed point on T? And here I'm going to have F will map from S to S, G will map from T to T. So do you think that if I have a function f that has a fixed point on S, that there's an associated function with a fixed point on T? What do you think? And if so, what would that function be? What would be the candidate? Yes?
Seems like it should exist, and the candidate could be like some composition.
Yeah, it should be some kind of composition. So if you think of what's going on, here's S, and we have a map f from S to S. I've never taken a real algebra class, so I apologize if the algebra diagrams don't look as good as they should. Down here, we have a T, right? And we have a map phi that takes us from S to T. That would be the map phi inverse. So phi inverse exists because I'm assuming we have an isomorphism. I'm assuming I have a one-to-one onto function from S to T. Now, let's say we have some function g from T to T. We can use this to build another function from S to S by just flowing down here. So we would have two natural candidates. One is we start with S, so we first apply phi, then we apply g, then we apply phi inverse. And this would take something in S and give us something new in S. You always have to be careful in these diagrams that you make sure that you go through them in the right order. Right? We're starting at S. G is defined on T, so we have to take something that exists in S and translate it into T. Okay? So this would give us a new function. Okay? So now the question is, what might be a good choice for G? So is there a choice for G such that this would be the same as F? Yes?
Can we just send it to itself?
I'm sorry?
Can we just send it to itself?
We could send G to itself.
Are we trying to build F? Are we trying to build G?
Right, we're trying to build G.
Right, so can't we just go the other way?
So good, so how should we do it?
Like, we're trying to build a function.
We want to try to build a function from T to T.
Shouldn't we build like phi inverse?
Yes.
Phi?
So we would start with phi inverse, then we would do F, and then we would do phi. And this will now take something in T and give us back something. What do you think the candidate would be for the fixed point for, we'll call this our function g. And let's say f of x equals x. So let's say x is a fixed point of f. Will G have a fixed point?
The t and t is mapped to x.
So we have some x over here. And what point do you think we want to look at down in t? Is it phi of t or phi inverse? Phi inverse takes something in t and gives us something in s.
We're looking for something in t, right?
We're looking for something in t. And I'm giving you a point x and s. So we would want phi of x. Right? So this is just following through and just seeing, if we have a candidate x, where would x live in t? It would live in phi of x. And let's see what would happen if we apply this. So we would have phi composed with f composed with phi inverse of phi of x. And now if we go through, what's phi inverse of phi of x? X. Now we take f and we apply f to x. X is the fixed point, so we get back x. And then we apply phi to that and we would just get phi of x. So the point of this is that if I, yes?
Isn't this a lot like, there's that thing in linear algebra where you multiply the matrix by
This is conjugation.
yeah, that.
So this process is called conjugation. Essentially, one of the ways to view linear algebra is you're just changing your basis to take advantage of the symmetries of the problem. So whenever you write down a matrix in linear algebra, you've implicitly assumed that there is a basis. And if you change the basis, the matrix looks differently. A matrix is a transformation. When you write it down on a paper, the only way you can write it down with numbers is if you choose a basis, and then you say, what does the transformation do to the basis entries? You don't actually have to have the matrix take an input and output it in the same basis. You can take an input in one basis and output it in another. Usually you don't want to be changing bases in the middle of a problem, but sometimes you might want to. Usually you will output in the same basis as you come in, and depending on the symmetries, you'll choose a different basis. I think we've talked about the equation of a ellipse or hyperbola, and if it's rotated, you want to just change your basis backwards. So the whole point of all of this is that if I understand what's going on with the function f from s to s, and I have an isomorphism between s and t, then I understand exactly what's happening to a very specific function on t. More generally, if I give you a function from t to t and I want to analyze it, if I have a map like this, I can say there is some f associated to it from s to s. And this would be my f. This is why I wanted to start this way. Because really, at the end of the day, let's say we understand one space, but we want to study what's going on in another space. If we have an isomorphism, we can pull from one space to the space we understand. Has anyone here taken complex analysis? It is being offered next semester, and there's a very good chance it'll be offered next year. One of the big things in complex analysis, one of the most shocking results in all of mathematics, is the Riemann mapping theorem. So Riemann mapping theorem. Say omega is open, simply connected, and it's not equal to the entire complex plane. Then there exists an infinitely differentiable complex isomorphism from omega to the unit disk d. So I give you something like this, and I can construct an infinitely differentiable map from this set to this set. I can even have it pointy in places. And in some situations, I can even extend the map to the boundaries. What this means, why do we care about something like the Riemann mapping theorem, is it says you probably do not want to understand, you probably don't want to directly work with this space. But because we have the existence of some map, we can basically pass problems on that to problems on the unit disk. So this goes very similar to stuff we did in the first week of class, where we talked about log tables. We only need to have log tables for one base, right? Because we have the change of base formula that allows us to pass from one base to another. We talked about how we only need to have tables for, say, the standard normal. If you want to calculate probabilities of a normal distribution, if I give you another normal, you can standardize it and then use those tables. The whole point here is we want to reduce the analysis to one simple case and then just study the crap out of it. Okay? So the unit disk is a really nice space to look at. So the whole point here is that if we do look at just a simplex, it's really not that much of a loss in generality as long as we have a nice map from our region to the simplex. And this allows us to standardize notation. This allows us to just say, let's just look at this one setting, and it's hopefully a little bit friendlier. Okay? So this is why for the rest of the day, I'm essentially only going to live in triangle world. Okay. So let's say we live in Rn. How many independent directions can we have in Rn? N, right? As soon as you have n plus 1 vectors, they have to be dependent. If you have n vectors, they may still be dependent. So what I want to do is I want to choose right now, we'll start off by doing things in the plane. So choose 3 vectors in the plane. Or more generally, we'll be choosing n plus 1 vectors in n-dimensional space. I'm going to do a lot of the lecture just in the plane. Question?
What is the symbol?
Which symbol? Okay. So I'm going to do most of the lecture in the plane. So let's say we have 3 vectors. v1, well, I guess you have to do it v0, v1, v2. And so if the 3 vectors all lie in a line, this is not going to give me a triangle. It's going to be degenerate. As long as the 3 vectors don't lie in a line, they will span a triangle. So what I'm really looking at is maybe, v1 minus v0, v2 minus v0. Is basically translate all the directions by the vector v0. In some sense, I'm basically just saying, just choose the basis of my coordinate system to be at v0. So let's say I have 3 points here. So here's v0, here's v1, here's v2. Does this remind you of anything? Yeah, doesn't this look a lot like Sperner's lemma? And why we were doing things as 0, 1, and 2. Normally when you count, how do you normally count? Starting at 1. Cam learned when he was young that if he counts at 0, and I tell him you can only do something 3 more times, he could actually do it 4 times. Most people do not start counting at 0. Okay, 1, 2, 3. We're doing it this way because we have the v0 that we're subtracting. What do you think this side is going to correspond to down there? We're going back to what we did with Sperner. This is probably going to be the 0, 1 side. So let's look at the following space. Let's look at all t0, v0 plus t1, v1 plus t2, v2 such that the ti's are all in 0, 1 and t0 plus t1 plus t2 equals 1. So what I'm trying to do is I'm trying to represent points as a linear combination of v0, v1, v2. So if you think about it in the plane, Should I be using 3 vectors as a basis? Okay, 3 vectors as a basis is bad. They're linearly dependent. Do I have 3 independent variables in this space? No, I only have 2 because I have the condition t0 plus t1 plus t2 equals 1. So because of that condition, it really is a 2-dimensional space. So whenever you have something like this, it's always good to look at extreme cases to try to get a sense of what's going on. What would be a good choice for the triple t0, t1, t2? 0, 0, 1. Okay, so if you do 0, 0, 1, that means we have nothing in v0, nothing in v1, and 1 in v2. So that would be the point over here. This would be the point 0, 0, 1. And similarly, if we do 1, 0, 0, it would be down here. And if we do 0, 1, 0, we would be over here. There's another point that's really natural. One more point is extremely natural. I'm sorry? I already did 0, 0, 1, yes. So 0, 0, 1 was the next one that's really natural. We've done that, so we now need to go beyond that. What's the next natural one? Can't. 1 over 3, 1 over 3, 1 over 3. So essentially all ones, right? Up to the normalization. So what would that mean? The point 1/3, 1/3, 1/3. Where would that be? Yeah, in the middle. So this is 1/3, 1, 1, 1. Saves a little chalk. What if I look at points just t0, t1, 0? Where would those points be? Yeah, in the line segment down here. So this is the segment t2 equals 0. Or another way of saying it, this is the segment where we don't have any 2's. So this is the bottom line segment. All right, now we could do t0, 0, t2. What would that be? That would be this one over here. And how would I write that condition? So if I'm over here, that would just be t1 equals 0. So this is left side. And then the last one would be 0, t1, t2. This would be the right. And so you can begin to see the spurner coming into play. A nice exercise showed that any point in here can be written uniquely as a sum of this form. That if you had 2 different triples, t0, t1, t2, t0 prime, t1 prime, t2 prime, they can't give you the same point. Okay? And we'll need to use the linear independence of these. We're going to be assuming these are linearly independent. If those are not linearly independent, our triangle collapses down to a line segment, and it's the wrong dimension. So we're assuming we have 3 different directions. Every point here can be written uniquely. Okay? So this is going to be called a simplex. I think this is called the 2 simplex. I always get things confused because the notation is terrible in terms of we have 3 things, but we're talking about it as a 2 simplex. It's 2-dimensional. So the number there is coming from the dimension. All right, our goal is we're looking for fixed points. So we need to have a map from a space to a space. So we're going to want to have a map from the 2 simplex to the 2 simplex. And the goal is to show that such maps have fixed points. So do you think every map will have a fixed point? So give me an example of a map from the simplex to the simplex that does not have a fixed point. Right. So not all maps from, I think the notation is delta. Yes, from delta 2 to delta 2 have a fixed point. So give me an example of a map that does not have a fixed point.
You add a constant to your map.
But I've got to stay from the set to the set. I've got to map from the simplex to the simplex.
Could you do like T1, T2, or T0, T1, T2 goes to 0, or T2, T0, T1, and move that one?
Okay, so what do you want it to do? I want to send T0, T1, T2 to what?
To T2, T0, T1.
T2, T0, T1. All 1/3. Crap, maybe everything does have a fixed point.
Maybe just change one goes to 0.
What do you want me to change?
Just any of the ones in the second one to 0.
Okay, so change this to 0.
There's 0 in the first one, the elements. Right. And 0, 0, 0 is back to itself.
0, 0, 0 is mapped to itself, but is 0, 0, 0 in the set? No.
Fair.
But, what?
1/2.
One problem though is this always in the set? Right? You've got to map from the set to the set. And so you're giving me lots of examples of functions that don't have a fixed point, but they're not mapping the set to the set. The sum of the coordinates has to be 1, and they have to be non-negative between 0 and 1. The sum here is T1 plus T2. This would be fine if T0 is 0. So if T0 is 0, this is legal. But if T0 is not 0, it's not legal. Maybe everything does have a fixed point. Maybe the theorem is even stronger than we hoped. Have you ever seen the joke about the word assume? All right, so I'll say trigger warning, there could be some slightly profane language. All right. Whenever you assume, who knows what comes next? It makes an ass out of you and me. You are assuming something about this map. What are you assuming about this map? Well, yes, because if we're trying to find a fixed point from the space to space, the domain's got to be. Now, one thing is, you said that we're assuming the domain is the whole thing. As long as the domain is a subset, that's fair game. We want the map to be from the 2 simplex to the 2 simplex. If it's to a subset, that's fine. But what are you assuming in all these examples that you were giving? You're assuming a property about this function. What property are you assuming about this function? That it's continuous. Right? So far, every example you've given me is continuous. Anybody want to try giving me a counterexample, a function that does not have a fixed point, which is not continuous? Drop the continuity. Yes?
You can take that before where we switch one of the things and then just say that at the point 1/3, 1/3, 1/3 just map it to something like that.
Sure. So take T0, T1, T2 goes to T1, T2, T3, if not 1/3, 1/3, 1/3. And then, do you have a favorite point? 0, 1, 0, if 1/3, 1/3, 1/3.
What is T3?
Ah, crap. I hate the notation of starting at 0. Thank you.
But you want to change one of those.
Oh, sorry. Oh, no, I was right. Sorry. T1, T2, T0. Thank you. So here's an example of a function that maps the 2 simplex to the 2 simplex, and it does not have a fixed point. So the nice thing is, this is a really dinky example, but it illustrates that continuity is absolutely essential. So the question becomes, is this the only assumption we need? Is it enough to assume that our function is continuous? Will that give us the fixed point? Okay, so any questions on what we've done so far? We've got a counterexample. We've done enough analysis to say that it really is sufficient to study something like this. This is even though it looks like there's 3 variables, it really is only a 2-dimensional space. Now the question becomes, how do we prove that there is a fixed point? So rather than directly stating Brouwer's fixed point theorem, what I thought I would do is try to give you a sense of the discovery process. These fixed point theorems are extremely important. Sadly, there is a placeholder in the chapter that says essentially, talk about Nash equilibrium. Right? So fortunately, somebody in the class has volunteered to expand the placeholder. Right? These fixed point theorems have led to immense results in terms of proving the existence of certain things. Now, in practice, you want more than just a strategy exists. You actually want to be able to find it. The contraction map was a wonderful situation where not only were we able to prove a fixed point exists, we actually had a way to find it. And the way was the easiest possible way. Choose any point in your space and keep applying your function and just sit back and wait. Okay? It doesn't get much easier than that. Right? Which point should I choose? Doesn't matter. Now, in terms of the convergence, it could matter. In terms of how long you have to wait, it could matter. All right. So this becomes an interesting way to try to review what we've done before. So let's say we start off, we have a function f at t0, t1, t2, and this is going to give us as an output, let's say, t0 prime, t1 prime, t2 prime. Now, at a fixed point, all the t's equal the t primes. If we're not at a fixed point, what must be true? At least one is off. So if not fixed point, at least one differs. So the key idea is trying to figure out how we want to compare things. What might be a good quantity to look at? So one is we could look at the difference between tuples. So we would have, t0 minus t1, t0 minus t0 prime, t1 minus t1 prime, t2 minus t2 prime. More generally, we could go all the way up to tn. Right? I really don't see the need in going all the way up to tn. It's the same proof. How do we now use the fact that at least one of them differs? What would that mean?
At least one of those is non-zero. One of the individual differences.
Okay, so at least one of the individual differences is non-zero. Could it be exactly one is non-zero? So could they all be equal except for one which is causing trouble that we just have to throw away? Why not? They have to add up to 1. That is a remarkable fact. In general, if I give you 2 tuples, is it possible for them to differ in just one place? Yes. But because the sum is 1 here and the sum is 1, t0 plus t1 plus t2 equals 1 equals t0 prime plus t1 prime plus t2 prime. If they differ, they can't differ in just one place. Okay, let's explore this a little bit further. What can you tell me now? What can you say about how they differ? Yes?
The sum of the differences must be 0.
So the sum of the differences must be 0. What would that mean if the sum of the differences must be 0?
The tuple must sum to
I cannot argue with that, but it's not as useful as other statements. What does that tell you about the differences? So the sum of the differences must be 0. What must I have? I'm sorry? I must have a positive and a negative, right? Some of them could be 0, but there has to be at least one that's positive and at least one that's negative. So what we can do is we can look at the index, which is the first one, which is negative. Look at first index where ti is less than ti prime. Let me make sure I want to do it this way, or if I want to do it where it's greater than. I want to do I think I want to do it this way. I want to do greater than. So we look at the first index where ti is greater than ti prime. If I give you something that's not a fixed point, will there be a first index? Yes. So again, the hardest part in these problems is trying to figure out what quantity to study. In some sense, that's where the real genius is. My advisor told me that there was a project he was working on where it took him and his postdoc 6 months to find out what was the correct quantity to look at combinatorially. The postdoc told me it took 9 months. So there may have been some time the postdoc was working before he went to the advisor in frustration, and then maybe it was 6 months from that point onward. But the hardest part was figuring out what is the right thing to study. This is why I do not want to just jump to and go through this at warp speed. I really want to try to go through the thought process as to how do you come up with these ideas. Okay? There's got to be a first index. So what we can do is we can assign an index to everything that's not a fixed point. So if t0, t1, t2 is not a fixed point, let ind for maybe index of t0, t1, t2 be the first index such that ti is greater than ti prime. And ti prime is the output. That's going to be the f of the t's and the ith component. Okay? So is everyone clear? If I'm not at a fixed point, just assign the value of the first index that differs. What should I do if it's a fixed if there's a fixed point? How should I define the function? So one possibility is to define the function to be infinity. Bless you. Any other choices for the function?
3.
I'm sorry? Yeah, for this problem, 3 would be fine. 3 is essentially infinity here. All the other labels are 0, 1, 2. If you see a 3, you know that it's the fixed point. Or what I could say is, I'm only going to define the index on functions that don't have fixed points. Our goal is to prove the existence of a fixed point. If my function has a fixed point, do I need to go through an argument to prove the existence of the fixed point? No. So we can assume that our function doesn't have a fixed point and look for contradiction. And if the function doesn't have a fixed point, then this map will be defined for all indices. Is this map continuous? No. It's integer valued. So as soon as you have something that takes real inputs and outputs integers, you should be extremely worried about it being continuous. There is an integer valued function which is continuous. Yeah, if we assign everything to one integer, it would be continuous. So in general, the index function is not going to be continuous. But maybe if it's always the same index, that's the first. Okay? So the question is it actually possible to come up with a map such that it's always the first? Because there should be some point, let's say we always want I equals 1 to be the index, and we just want everything to be sent to 1. Yes?
Well, if it's the first positive one, you know that you have to, the sum of the differences has to be 0. That means if you have a negative one, like the second component or something, then when you...
Yeah, I was going to say, if you take a 0 in the component corresponding to the index of 1, then you know that can't be the first index where it's greater. So there's no way to create an index function that's continuous. So if our goal is to use properties of continuity on the index function, we're dead. But it wasn't continuity of the index function. The index function is an auxiliary function designed to help us. It's the original function that we're going to assume is continuous. And we've basically shown that if we don't assume our function f is continuous, it doesn't have to have a fixed point. So restricting ourselves to the space of continuous functions is not a huge deal. Okay, so the camera doesn't really want to swivel back, but I do. I want to look back at this over here. Come on, camera, there we go. Come on, come on. All right, so I think it's close enough. All right, so let's look at this triangle, or maybe since it doesn't really want to, can I erase the central part of the board? So I'll draw a huge triangle. All right, this over here. Oh, I really just. Oh, all right. No. So if I walk straight at it, it's me. All right. So let's try it again. All right. So here's our triangle. This over here is V0. This is the point 1, 0, 0. This is the point V1. It's 0, 1, 0. And up here is V2, which is 0, 0, 1. Let's assume we have f from delta 2 to delta 2, and it has no fixed point. And we'll assume f is continuous. Because if it's not continuous, we know there's the possibility of no fixed point. Let's look at our index function. Now, if you're going to figure out the index function, you really do need to know what f is, right? Without knowing f, it's going to be kind of hard to analyze the index function. But maybe there are some places where we can analyze the index function. Maybe not perfectly, but maybe we can glean some information about the index function. Where do you think might be a good point to start to analyze the index function? Where might you start? Where might you look first? V0. So let's see what happens. We apply f. Is this a fixed point? No. We're assuming f has no fixed points. So we know that 1, 0, 0 is mapped to something else. Is it possible that the first coordinate stays 1? No, because the sum of the coordinates has to be 1. If the first coordinate stays 1, it's going to be mapped back to 1, 0, 0. So what would be the value of the index at this point? 0. So we all agree we would assign 0 here. Let's look at this point now. 0, 1, 0. Where is the first coordinate for 0, 1, 0 where the index is not going to equal? It's going to be 1. It's going to be the middle coordinate. What's this beginning to look a lot like? It's looking a lot like Sperner. All right. And then we can have arguments as to whether or not we should be doing V0, V1, V2, or V1, V2, V3 in terms of what should the labels of our triangle be. There are advantages and disadvantages to both. Up here, a similar analysis will give us that this is a 2. Great. We have figured out what the index is at 3 points, only uncountably many more to go. Where should we look next? I'm sorry? Okay. So we could look at the center, which is 1/3, 1/3, 1/3. I haven't told you what f is. Do you know anything about what value might be assigned there? No.
What are the edges?
Yeah, let's try the edges. So let's say we're on the bottom edge. So if we're on the bottom edge, we're on points t0, t1, and 0. And this gets mapped to something, say, t0 prime, t1 prime, t2 prime. What do you think our goal is? What do you think we want to show can't happen on the bottom?
Can be 2.
It can't be 2. What would it mean for it to be 2? It means the first index where this beats t2 prime, or so beats the primes, is the 2 index. Well, but this is 0, and this is non-negative. So it can't be a 2. So what do we know about t0, t1 going to t0 prime, t1 prime, t2 prime? It's got to be a 0, 1. So the value of the index along here is index has to be in 0, 1. Similarly, what would we get if we looked over here? 0, 2. And last and least, that's not horrible. And then this would be 1, 2. And now, what's true on the inside? I think shrugging shoulders is the best we can do, right? We don't know what f is. I can't do more than just say it's in 0, 1, 2. Okay. I know I've mentioned the result numerous times, but the script now calls me to say, what should we think about using now? Sperner's lemma, right? Sperner it. So we can put in a triangulation. And what the triangulation will tell us is that there will be some point where we'll have a triangle where the labels are all distinct. So what we do is we triangulate this. We put in triangulation, we put in a bunch of points, we break it up into triangles. By Sperner's lemma, one of these triangles has 3 different labels. What do you think we do now? Yes?
Look inside that triangle.
So we could look inside that triangle, but the problem is I can't use the index argument again. I don't know that this side is going to be just 0, 1s. Right? So this is where things get difficult. I have the existence of a 0, 1, 2 triangle, but I don't know that if I look inside this. I'd love to say, let's Sperner it again. But Sperner needs that the boundaries have labels that are all one way. And if I try to apply it to this interior triangle, I don't know that that's the case. All I know is anything on the inside is labeled 0, 1, or 2. So this is the last key idea we need for Brouwer. We will not get to Brouwer today, sadly, but we will at least get to state the idea. What should we do? So let me give you a little bit more of a heads up as to how we did this. Let's divide this into n equal places. All right, and we'll divide this into n equal places and this into n equal places, and we'll get all these different triangles like this. Okay? So we take a mesh where we divide each side, n, n, n. And that will give us the existence of a triangle. Maybe the triangle is here, 0, 2, and 1. this triangle is going to have a certain size. What size would you love that triangle to have? 0. Because essentially, if that triangle is 0, then it's saying the first index, which is greater than, how am I doing that? That basically, in the limit, this should be a fixed point. If you have a point which, the function is continuous, and the first index, which differs, is the 0th and the 1th and the 2nd, things are blowing up. This is giving you a contradiction. It's going to violate the fact that your function is continuous. Because as I approach it, one way, it's saying the 0th should be the first one that differs. Another way, it's the first that should be the first one that differs. Another is the second should be the first that differs. How can I make the triangle smaller? Make the mesh smaller. So now instead of doing n, do 2n. And, cut everything in half. Will my new triangle be inside this triangle? Not necessarily. Maybe it's over here. Now what do I do? Smaller. Divide them all in half again. And I get another triangle. I keep doing this. And now I have a collection of triangles. What do I know about that sequence of triangles? It converges. Why? We learned it the other day. What names do we attach to this? Bolzano-Weierstrass. There was a reason I was saying, does anybody want to see Bolzano-Weierstrass? It's going to be playing a key role here. We're going to have a sequence of triangles getting smaller and smaller and smaller. And then the goal is that there will be a sequence, there will be a convergent subsequence. And then we'll have some point here where if we look at what is the first index when we apply f to that, which differs. If I come across it in this path, it's going to be 2. In this path, it's going to be 1. In this path, it's going to be 0. And that's going to violate. You can't have the first thing being all of them. And that's going to essentially be the proof of the Bauer fixed point theorem. So I know I did not state explicitly what the Bauer fixed point theorem was today. Yes?
We say where we use the continuity of f in this proof.
Right. It's basically right here. So we will do more of this either Wednesday or potentially Monday.